So, we're learning about probability today. Fundamental counting principle is up first. Let's do this. So, Ernesto's got 5 shirts, 4 pairs of pants, and 3 shoes. The total number of outfits Ernesto can make consisting of 1 shirt, 1 pair of pants, and 1 shoes is... I love this. I once tried to figure this out by saying, I wonder how many different things I need to wear a little something new every day to work. Okay? How'd you do it, guys? Yeah! Excellent. Really great. Really great. 3 slots. 1 for shirts, 1 for pants, 1 for shoes. 5 different types choices for a shirt. Times 4 different pairs of pants. Times 3 pairs of shoes. What do we got? 60. You guys did this in 9th grade. You're good with this? Excellent. That's the only time we're going to do it now. I'm going to expect that you know it. When different events are taking place independently, you are multiplying. That's how it really works. If you want to see where it all comes from, I'm telling you right now, all of this comes off tree diagrams. And we could spend our time making a tree diagram. Guess how many branches it would have? 60. If you want to, you can. I don't recommend it. Some of the answers in this class are like 9 million. Yeah, I'm serious. You could be there for a while, but if you want to, we'll give you some paper. Anyways, let's go. Here we go. So now, practical applications of problems like this are license plates. Okay, how many like spots do we need on a license plate to accommodate like all the people that live in a particular county? Find the number of arrangements that can be made from the letters of the word think. Very nice. Yeah, you were close back there, just a little bit off. Alicia, brilliant. There's 5 spots. How many choices we got for that first spot? What about for the next? Why can't it be 5 to the 5th? Because we are not reusing letters. If we were allowing, like, if you allowed me to make a word from this with just 5 T's, I completely agree with you. The answer is 5 to the 5th. But you choose, let's just say the first letter was a K. K is gone. We got 4 choices for the next one. Do you understand? Why can't you reuse? Oh, because find the number of different arrangements that can be made. It should say without reusing the letters. It really should, because people can get that confused. I agree with you, Max. It really should. And because it doesn't, I almost agree with you that you have a valid point. But you get what they really meant. Okay? Now, this could get really annoying. Suppose there were like 150 letters. Can you imagine writing that out? Marquita, you're amazing, girl. You are amazing. Yeah, that's the same thing as saying 5 factorial. Break out those calculators. Bust them out. Man. Yeah, it's 120. Let me show you where to go, though, so that you know in the future. 5, math, scroll all over to PRB, stands for probability. Scroll down to the, yeah, just like that, 120. Oh, Let's do B. Arrangements if there's only consonants. You know what a consonant is, right?
Anything not to think about?
Yeah. Wayne, if I were you, I'd leave her alone. I'm just saying. Here we go. 4 factorial. 24. Very nice, Malik. Thanks, buddy. That's it. That's all we got. That's all we got. So here's the deal, guys. This is the beginning of our conversation, and this is the theme for today. When does order matter in counting stuff up, and when does it not matter? For example, how many unique arrangements can be made? What happens if I switched this A and that A? Would I get a unique arrangement? No, I get the same word. How would you know if I had chosen like this A and this A in that spot, or the reverse? You don't know. You don't know. So mathematicians had to find a way to try and figure out how many unique combinations could be made and taking out the double counting without having to list everything out. Go. Oh, it doesn't work like that. I wish it did. It's an excellent idea, though. Go. Count the letters. How do you count them? What do you mean, just not enter them into the factorial? You don't enter them in. The problem is that they're saying how many unique arrangements can be made from how many letters we got there? 8. You're suggesting that I take out 1, 2, take out 4? Then I'm only really choosing I'm only really going to choose 4 letters. I wouldn't get that word. Let me show you how you do it. You say to yourself, well, there were 8 factorial ways we could have arranged this. Yeah, Alicia. Nope. We are going to divide out by the repeats. Since A repeats 3 times, this is the number of different ways A's could have repeated themselves, and we're going to divide out by that. Guess what else I got to divide out by? Very nice. Why? Good. Yep. And so I got to show you how to enter this into the calculator because people get this all messed up. Here's what you do. You know what? I'll make this link down there. We're going to do 8 math, PRB, factorial, divided by, and in parentheses we're going to put this so we could group it together. Oh, that's annoying. 2 math. Let's see if you get the same thing. 3,360. Is that a big number? Yeah. Is that like really big? Okay, good. Yeah, it's not that big, to be honest with you. That's actually relatively small in the world of probability. Let's play again. Sorry about that. Hold on. What'd you want, Max? What? Sure, I'll just show you up there. Look, all I did was our normal factorial business. It's just that to catch everything underneath the bottom, I had to group it together with parentheses. It's like all of it is there. Otherwise, what it'll do is order of operations. It'll do 8 factorial divided by 3 factorial, and then it would multiply that by 2 factorial. If there's no repeats, you just do it like the think question. It's just a factorial. Let's do Schenectady. Schenectady. Schenectady is not a made-up word. It's in New York. Guys, how many letters in Schenectady? 11. How many repeats? 2 E's and what? Tell me, how much is this?
Wow.
900. No. 9,979,200. Can you believe that? That's crazy. Is that a big number? That's a pretty big number. It's a lot of dough. It's a lot of dough. Okay? This in. Okay, permutations. You know what you want to know about permutations? Order matters. Order matters. What do I mean by order matters? You use a permutation calculation when you are talking about running a race and finding how many different ways you can select people to get first, second, and third. You use a permutation calculation if you are having a class election and you are trying to figure out how many different ways you can elect a president, a vice president, and a treasurer. That will be very different from what comes after it, and that's called a combination. In a combination type question, order does not matter. An example of that will be something like in a class, we want to know how many different combinations of 5 partners for a lab group can we create. You understand? Order doesn't matter. Whether I select, I don't know, Malik, Wayne, and Mungi, or Mungi, Malik, and Wayne, it's the same group. But if you guys are trying to run for president, selecting Malik president, Wayne vice president, Mungi treasurer is different than Mungi president, Wayne vice president, Malik treasurer. When order matters, president, vice president, and treasurer, permutations are used. Let's do this first problem. How many ways can a club select a president, vice president, secretary, and a treasurer from 16 candidates? I mean, here's what we really got. It's no different than what we first started. President, VP, secretary, treasurer. Obviously, you pick somebody. They can't be in two positions. So, how many choices we got for a president? How many for a vice president? You guys are amazing. Suppose there were 250 million people in the class. Would you really want to punch that into your calculator? Not really. So we invented a shorthand way of describing this. It looks like this. 16p4. Start at 16 and multiply the first four numbers downwards. That's what that means. Anyways, let's use your calculator. Turn it on. Type in 16, math, scroll all the way across. Holy cow. Did you know that? There was 43,000 different ways this could be done. 43,000. It's the same thing. Watch this. 16 times 15 times 14. 16 times 15 times... Same thing. Okay. The answer in both cases is 43,680. Good. Let's play again. I'm sorry we're going so fast. I just want to make sure we get through everything. This is a very real example for you guys, right? You got 5 subjects. You're deciding what order you should start them in at home because as you go through your homework, you get more tired and tired. So you might want to do the one that's most important first while you still have energy. If you are, right, if you need to choose 4 of the, how many different ways can you choose to do 4 of these 5 assignments? And order matters. How do you use it? What do you plug in? Besides doing the long way of listing them out, go, Makar. 5p4, excellent. Great job, girl. That's the same as doing this. Times 1. And so here, it's a great question. Herein lies the difference between this and the factorial, right? Factorial would take you down to 1. This one stops at a certain point. What's up? Anybody questions? Nah? Let's play again. One more time before we get to combinations. You're doing really well today. Really well. One more time. What about this one? 12 people run a race. You guys are amazing. 12p3. Let's punch that in our calculators. Tell me what you get. Yeah, 1320. Guys, finally, combinations. Combinations. You know what you have to remember about combinations? Order does not matter at all. Order does not matter. The way I always think of these questions, like how do you know if it's a combination question? I say to myself, think about science class. Yeah, think about science class. Lab partners. Right? Think about science class and lab partners. If it's a question where you are just putting together groups of people and it really doesn't matter about the order, there's no positions like president, vice president, treasury, there's no like winning a medal first, second, and third. It's a combination problem. But if you are, it's a combination problem. But if you are selecting people for positions, it's a permutation problem. So guys, let's do this. I wanted to choose a problem that I thought was very real. Some people in here play a lot of cards. The first thing we have to do is, and it's very important, every single person in here should know how many cards there are in one deck. Good. There are 52 cards in one deck. How many suits are there? 4. And what are the suits? Good. And how many cards are there to each suit? 13. That should be standard for every single person in here. Cards are drawn at random from a 52-card deck. Find the number of different 5-card poker hands possible. Here's what I want to say to you. Suppose I pull out 4 aces and then a queen. That is the same hand as a queen and then 4 aces. Do you understand that? It was just a different order, and that's what the combination calculation takes into account. It takes out all of that doubling. So let's do this. Any 5 cards from a deck. You know how many poker hands are possible? You're gonna freak out when you see how many different hands there actually are. There are 52, McCarm. Yeah, 52C5. Break out your calculators and enter that in. Somebody read that number for me. No, not 259 million. Wayne. Okay, 2598 what? 960? That is 2.5 million different hands possible. That's 2.5 million hands, and the calculation took out doubling. That's crazy. And here we go. The compound events. Ready? Suppose now, tell me how many different ways can I pull 3 aces and 2 kings out of a deck? What this says is, from the collection of 52 items, the number of different ways I can have 5 of them in my hand is 2 million, right? How many aces are there? 4C3 times, it's just like that beginning problem with the counting principle. It's like, how many different ways can I put on pants? And then shirts. Times, how many kings? 4C2. Now tell me, what is that? It is 24. Now let me explain. Does anybody understand how it's 24? Now let me explain something to you. Dude, if we are playing poker and you look at your hand and you see 3 aces and 2 kings, what do? You go all in. You bet everything you have. You know why? Do you know what the rarity of pulling this actually out is? The chance of this occurring there were 202,598,960 different possibilities, and you have a hand. There were only 24 of them. That's the chance. It's like 1 out of every 2,000 times that should occur. You bet everything you got. If you have the pink slip to your car, you put that down as well. Okay? If you know what? You absolutely can lose, and that's what I want you to understand. Absolutely. But suppose you have 1,000 cars. Okay? If you continuously play this game, where you bet the pink slip to your car with that hand and all the money you got, you're going to be a very wealthy man in the end. If you can afford to do it and last that long. You know what I say? You're in trouble. That's something to think about. And that's why poker is different than a lot of other games. Okay, 4 queens in any other card. Nope. The second number always has to be smaller. It's 4C4. Nope. There's not 52 cards left. Good job, guys. 48C1. Tell me how much that is. What is it? 48? Good. And finally, we got one last one. 5 spades. 5 spades. How many different ways can you pull 5 spades? Very nice, guys. 13C5. Tell me what that is. And then we got one more problem and we're done. What is it? 1,287. Very last problem, and then you're out of here. There is a question 12 on your sheet. You don't even have to answer it. Just tell me whether you think it's a permutation or a combination question, and you're done. Very nice.